Hello, we are continuing our lesson on probability. This lesson will be on events and the rules of probability. So if you saw the last video with the basics, then that ties in very closely to this video. And you'll see some overlap. Takes me a second to get everything situated. Here we go. All right, so talking about events, and I mentioned events a little bit in my last video, so if you watch that, then you probably kind of already know what it is. We're just going to take a deeper dive into it. A sample space is a list of possible outcomes. So the sample space of a deck of cards would be, and you might not want to list all of this out because there's 52 possible outcomes, so that's kind of a lot, but we could summarize that by saying each card in the deck. So 2 of hearts, 2 of diamonds, 2 of spades, 2 of clubs, 3 of hearts, 3 of diamonds, 3 of, on and on and on. So it would be every single card in the deck would be the sample space. The sample space of a die, and I talked about this one in my last video, die is singular for dice. Like mice is plural, and anyway, mouse is not. Okay, so die is singular for dice. The sample space of I should be more specific here, it is a 6-sided die. So there can be more sides than that, but in general, when I talk about dice, I'm talking about the 6-sided die. The sample space of that will be 1, 2, 3, 4, 5, 6. And you'll notice that I put little braces around it, and that just shows that this is a set of numbers. So whenever you see those little curly braces, that's a set. An event is a subset of the sample space. So this one is a set, which includes all of the possible outcomes. An event is a subset, so it's maybe a few of the outcomes from the set. So it's kind of like a little offshoot. We use Venn diagrams to visually represent relationships between events. So the sample space represents the rectangle around the Venn diagram, and it represents every possible outcome. And then each event is drawn as a circle, and sometimes they overlap. So when events overlap, then that means they have outcomes in common. And so we call that not mutually exclusive, which is kind of confusing. That's why I'm pausing, because I'm like, not mutually exclusive. Anyway, I was getting myself confused, because if they're not mutually exclusive, then that means that they do overlap. Anyway, mutually exclusive means that the events have nothing in common. So I really probably confused you with that wording, but if we just kind of skip down to this part, mutually exclusive means that they have nothing in common and the two circles will not overlap. Okay, so here's a picture example of a Venn diagram. And these are maybe, fruit. Okay, so there looks like colors of fruits, and in this side we have red, and in this side we have orange. And you can see that in the middle a pepper can be red or orange, red and orange, and a tomato can be red and orange. I didn't know a tomato could be orange. I believe them. So this is, excuse me, their overlap. These are the two events. And then this is the sample space. So if we were to say, they didn't for this example, but if we were to say the sample space is fruit, then we would put all the fruit that's not red or orange outside here in the sample space. So what's a fruit that's not red or orange? Blueberries, bananas. So that they didn't put that on there, and that's probably not what this was, but I just wanted to kind of show you that if you have a sample space where something doesn't qualify as one of the events, then you're going to put it outside the circles in the box. So a couple things I want to point out with this Venn diagram. Some relationships that you're going to see among events are complement, intersection, and union. So the complement means they do this little tilty sign. It means not the event. So it is everything except, I'm running out of room, the event. So if I were to say not red, then we would list these two and these, but I threw those in. Or if I were to say not orange, then we would say these two. So these are complements of each other. They kind of complete the set. So for example, you could do, if you're looking at couples, then maybe, you know, some couples are opposites. Opposites sometimes attract. So if you look at, for example, me and my husband, I'm short and I have brown hair and green eyes and I don't know. Yeah, we'll go there. And then my husband is tall with blonde hair and blue eyes. So we're very opposite, and he's everything I'm not, or he has everything I don't have. I can't lift heavy things, he can. I can't reach high things, he can. He can't do little tiny meticulous detail things with his fingers, I can. So we complete each other. We're complements of each other. And then an intersection is the, you might see this symbol. Yeah. For intersection, it's kind of a upside down U. And if you see like A and then that symbol B, that means A intersect B. That's how you would read that. And you might see A and B, or it might be written A and B, which means that both A and B occur. So for example, in this Venn diagram, that's going to be the overlap of the two events. So A and B occur in peppers and tomatoes, red and orange. And then the union is a U, and you read that A union B. The wording for union is or, and it means either A or B. It's a little less restrictive than an intersection. So when it says union, that means that you're combining all of the elements together into one set. So if I were to say red fruit or orange fruit, that would be these, red fruit or orange fruit. Either one is fine. So if I were to say, I wanted you to go pick up my lunch or something, I don't know, that's ridiculous, but, and I either want white cheddar poblano soup or broccoli cheese soup, then it's a little less restrictive. You could come back with either one and I would be happy with it. Whereas if I said, I want white cheddar poblano soup and broccoli cheese soup, then you would bring, anyway, that's a weird example. X that. That's a weird example, but I'm trying to explain that a union, ooh, I have a better example for union. Let's say you and your significant other are moving in together. So like when Jared and I got married and we moved in together, our marriage was a union of two people. And when we moved in together, we brought all of our stuff from both of our two houses into one house. So the union of our relationship brought all of our things into one set. So that's a good example for union, not the soups. Whereas intersection would be a little more restrictive. It has to be the things that are in both his house and my house. Like, for example, I had a casserole dish and he had a casserole dish, and I don't know, it's getting weird again. Let's move on. Basically, the key thing I want you to see here, I don't know why it's coming off weird with my examples, but the intersection is here in the overlap, and the union is gathering all the items. Long story short. Moving on. Use the table and the information below to determine the number of outcomes possible. So we're not finding the probability, we're just counting how many outcomes are possible. So I think in your notes, this actually took up 2 pages. For some reason, this part went over into the next page. I'm sorry about that, so you have to go back and forth. I fixed mine because I had a hard time going back and forth. But here's the table. So there's 2 18-year-olds, 3 19-year-olds, 1 20-year-old, and so on. And we're letting these be the events. So event A is the event that a student is over age 20. Event B is the event that the student is under age 22. And event C is the event that the student is a teenager. So we're not finding probabilities, we're just counting how many possibilities there are. So when it says not C, you might see this as not C. C is the event that a student is a teenager. So if I were to say not C, then it's everyone except teenagers. And that is these guys here. Now keep in mind that we're finding how many outcomes there are. And be careful when you're reading the table. These are ages, not how many outcomes. They're just ages. These numbers represent how many of those there are. So the people who are not teenagers, there's 5, sorry, I don't know where that tweet's coming from. 6, 7, 8, 9. There's 9 people who are not teenagers. The next one is A and B. So event A is that the student is over 20. So that's these people. And then event B is the event that a student is under 22. So that's these people. Let me just actually circle that. Under 22 are here. Over 20 are here. I made a little Venn diagram. Look at how cute that is. So which part of the Venn diagram represents and? Over 20 and under 22 would be the people who are 21. And there are 5 people. Here we go. Okay, next one, A or B. It can be, the student can be over 20 or under 22, which if you'll recall, the union means that it could be either one, so it's a little less restrictive, and that means that it's all of them. Over 20, under 22, yep. So either one. So a person who is 23 is either over 20 or under 22. They qualify as one of them, so we're good. And then 18 would be either over 20 or under 22, so it counts. So it's actually all of them. And if we add those up, we get 5, 11, 13, 14, I believe, hopefully. And then the last one is A or C. Excuse me. Erase this. A is the event that the student is over 20. And C is the event that the student is a teenager. So we're counting the number of outcomes. This will be an example of mutually exclusive. The Venn diagram has no overlap. So if this had been, it wasn't, but if this had been A and C, then we would have 0 outcomes. But since it's A or C, that means it can be one or the other. We're just going to total those up. So 5, 10, 11, 12, 13 outcomes. Isn't that neat? All right. The Venn diagram of mutually exclusive events looks like, and I've already kind of talked about it a little bit. This, if you turn your head sideways, this would be a picture of that. So you do your little rectangle, and then you draw 2 circles that have no overlap. We would call this event A, event B, and then this is the universal set, which is the whole sample space. And that's it, mutually exclusive. So some examples of sets that are, or events that are mutually exclusive would be, well, I did one up there where the person was either a teenager or over 20 or whatever it was. So that would be mutually exclusive. That's an example. So we can kind of point to that example. Another one would be on a die, rolling a 1 or a 2. Those are going to be mutually exclusive. There's no overlap. Or cards. If you're looking at hearts or diamonds, those are totally different. No overlap. So in the numbers, there's like they both have 2s, but it's a 2 of hearts and 2 of diamonds. Anyway, anything that has no overlap. So let's move on to the rules of probability, because a lot of that is going to play into this. So we're kind of jumping back into probability. Remember that E represents an event, and if we find P of E, that represents the probability of that event. So remember back in my last video, we did P of 2. That was the probability of rolling a 2. So that 2 would be the event. And then we've already talked about OR a little bit with unions, and we know that OR is a union. We know it means it can be one or the other. And I had to change this example in your notes because I believe it was a typo. My iPad's frozen for some reason. There we go. Okay. So I went ahead and just changed it to how many outcomes represent the ages of students who are 18 or 21. So that means that the student can be 18 or 21. And that would be 7, age 18, age 21, 7 possible outcomes. And then if I counted the total number of outcomes, that would mean that I'm adding all of these up. 5, 6, 11, 12, 13, 14 total. and I were to compute the probability, remember from my probability video that you take the favorable outcome, which is A or B in this case, and divide it by the total. And then remember we simplified that. So half of the students are either 18 or 21. And that leads me to, sorry, I paused because I'm just double checking my math. That leads me to the little box down below. I don't know why this keeps freezing. This is the probability rule for mutually exclusive events. Remember, that means that the events have no overlap. So for mutually exclusive events, when you see the word or, that means you're adding the probabilities. So where did this rule come from? I don't want you to just memorize the rule. I want you to be able to think back to what or means and how we find the union of those two events or those two sets. So if we go back up here and we look at this example where it says either A or B, I totaled up the frequencies from event A, which was age 18, and event B, which was age 21, to get 7. So when I looked at event A, there were 2 people. When I looked at event B, there were 5 people, and I added those to get 7. So whenever you're finding the probability with the word or in it, you're actually just adding the probabilities. So let's take a look at this one a little bit separately. If I were to go back and redo this and say, what's the probability of a student being 18 or 21, probability of 18 or 21, I could find the probability of each event, and I would get 2 out of 14 and 5 out of 14. And if I added those together, there's that 7 out of 14. So when you see the word or in probability, it means that you'll be adding the 2 probabilities. Isn't that so neat? How it all ties together. This is why I love math. And you'll notice that I didn't reduce before because I wanted to keep the denominators the same. You can reduce as your last step if you wanted to. Well, you'd have to. So when events are mutually exclusive, you can just add the 2 probabilities, and that's your probability. Tongue twisted. The value changes if the events are not mutually exclusive, because we need to account for the overlap. We don't want to count the overlap twice. And so what we do is we're going to have to subtract one of them out. And I'll show you an example. Let's go to the next page. Sorry. Here's this example with the cards, and I put another picture in there so you could see them in case you're unfamiliar with cards like I am. I love Yahtzee, so I'm good with dice, but never really been into cards. Okay, so let's look at this problem. For the first part, we're just counting how many there are. So we're kind of getting ready to do the problem. Count the number of red cards. Half of them are red, and there's 52 cards in the deck, so 26 are red. How many are kings? 4 of them are kings. Are there any kings that are also red? Yes, 2 of them. So let me show you here what that looks like. Here's the reds. And then here's the kings. And you can see here, there's some overlap. So it's kind of like two on a Venn diagram, it's like the two circles. Here's a circle, here's a circle, and they overlap right here. So that overlap is where there's two items that are in both sets. I'm getting excited, so I need to slow down in my talking. So what we need to do is we need to subtract out the two that overlap. So when we're finding the probability of drawing a red or a king, the probability of drawing a red is 26 over 52, or a king, but we need to subtract out the two that overlap. And we get 30 minus 2 is 28. And then reduce by 4, I believe. And then if we were to write that as a decimal, we would get about 0.54, which is 54%. So the point of that is when there's overlap, you have to subtract that out so that it's not counted twice. Because we counted it here and we counted it here. So this means we need to subtract one of them out that we counted twice. And then complement, if you'll remember, complement means everything except the event. So if I were to say the complement of red, then you would say the complement of red is black. Or the complement of aces would be everything that's not an ace. And then also, what is the highest possible value in probability? You might remember this from my previous video on probability. The highest possible value in probability is 1. Because 1 relates to 100%, and 100% is the highest we can go in probability because that's the highest possibility of getting an event. So if I were to say, what's the probability, I don't even know, of the sun shining tomorrow? I mean, I guess unless the world ends, then it's that's a really terrible example. I'm not doing very well on examples this time. So something that is very sure 100% to occur is a probability of 1. Long story short, I don't know why I cannot come up with an example. Whoops, kicked something. Moving on. So if the probability of an event occurring is x, then we can find the complement of x knowing the highest possible value. So if the event is x, and we want to know the probability of not x, then we can do 1 minus x. And here's a better example. If you score an 85% on a test, that means that you got 85% correct. What percent did you get incorrect? You might know automatically, oh, 15. But where did you get 15? You know it's the value that completes the score. So since you didn't make a 100, then you know that 15% is what's left to complete the score. 15% would be the complement. All right. I don't know why I can't think of something that has a 100% or a 1 probability. I've gone blank. We'll just move on. So here in this box is another probability rule. If you take the event and the complement of the event and add them, you get 1. Or likewise, if you subtracted this over, the probability of an event occurring is 1 minus the complement. So you can kind of use that to help you. For example, down here we have this table. We want to find the probability of a student being younger than 23. So instead of adding all these values, which adding isn't difficult, but just to be a little bit faster, instead of adding all these values, I can actually do 1 minus the probability of the person being 23. And that would give me the rest of the probability, the rest of the values. 1 minus 0.071, make sure I type that in right, is 0.929. So let's just take a second and let's actually add these and make sure that they add up to 0.929. I actually got 0.928 for the sum of these, but it might just be a rounding error for the relative frequencies. And if we were to even round that to 1 decimal place, because the data is whole numbers, so the rule of thumb is to round to 1 decimal place, then we could round that to 0.9, and this will be rounded to 0.9, and then they're the same. See? So instead of doing all that, finding the probability of someone younger than 23, you can just look at the person that's, or the probability that the person is 23 and subtract that from 1. Because when you add all these up, they should all add up to 1. So 0.929 plus 0.071, these all add up to 1. So when you do 1 minus this, you get the complement. Anyway, and remember, this is worded. We've also talked about the word and. This is a little bit weird on the wording here. I meant to write and, or this little ampersand sign represents the overlap in a Venn diagram. So just to kind of review that, we had 2 circles and represents the intersection. So this is and. Make that smaller. There we go. And the one we used for the example was red card or a king. And we noticed that they overlapped at the red kings. So that would be the intersection. So if I were to say, find the probability that a card is a red and a king, then we know that 2 of the cards represented red and a king. And then we would reduce that and be 1/26. That is all I have for this lesson. I hope you enjoyed it. Sorry about my weird examples. If you have any questions, please let me know, and I would be very happy to help. See you in the next one.